Hey everyone. So I bet before we talk about quantum computing, you're wondering what a computer is. Well, we think about how do we think about computers intuitively? What's the most naive approach to defining a computer? Well, it's a thing where we have some sort of question we want to ask, and we can't do it by hand. So we put it towards some sort of system or machine, and the machine outputs some sort of answer for us that is hopefully correct. That would be part of the definition of a good computer is that it gets the answer right. So within this naive kind of definition, there are a number of different devices which meet the criteria. The most simple is what's known as combinatorial logic, a combinatorial circuit. So a combinatorial circuit essentially just has some inputs and it maps them to a specified number of outputs. This is both size n. There are n inputs and n outputs. So we have a question, let's say, and we put something into the computer. Three inputs, let's say. And the computer kind of lies here. You'll see why I'm calling this f of x, or rather f of I, in a moment. And it maps to three outputs. These could be the numbers that are the sums that we're trying to perform. This could be yes or no questions. Is this number an integer? Is this number rational? It could be something outside of mathematics. It could be render a screen for me with these elements on it, maybe like a square, a triangle, and like a hexagon, right? So given n inputs, the computer will reliably and correctly return n outputs. Depending on the context of the problem, what correct is varies. So how would we implement this kind of thing? How would we actually build this thing out of hardware and software? Well, we can build that actually out of mostly just the hardware layer looks like this. Um, we have these circuits called Boolean circuits. And this is not the only way to build a combinatorial circuit, by the way, or a combinatorial program. It's the way we do it. It's the way we do it in most modern computers, just because it's the easiest way to do it from an engineering perspective. But this is one set of gates that we can use in order to build a combinatorial circuit. Um, so we can compose these gates together, and these are not the only gates, but this does form a universal set of gates, the composition of these gates here. So what we do is we take an AND gate, and maybe we compose it with a NOT gate, and we get something called a NAND gate. And believe it or not, through the combination of any of these gates together, we can do something like this too. OR takes two inputs, and it outputs something, and then maybe down here we'll have a NOT gate, and the output of the NOT gate will feed into the input of the NOT gate. Or we can put this through like an AND gate. Through the combination of these guys, we can build a computer or a combinatorial circuit that can compute pretty much anything that can be computed with this class of computers. There's a lot it can't compute, but an intuitive way to think of what these computers can do and can't do is every single one of these things, when we compose these Boolean logic gates together, um, corresponds to a function. That's why I was calling it f of x, where x is an input and the output of this thing we can call y. It maps a given x to a given y. In this case, there's multiple inputs. There's three inputs in this case. So we'd have x1, x2, x3, and it can actually map it to a singular input, or it can map it to two outputs, maybe this and this. So we can get y1 and y2 out of it. The number can be different of inputs and outputs, of course. Um, So, but yeah, this might be a little confusing actually up here because I said n inputs and n outputs have to be exactly the same. They do. If you give one input, it maps it to a unique output, but it could be something like this to one. This whole thing is one input, and this could be a yes or no question, 0 or 1, and it says the answer to this question with this input. This could be like a long, 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 long number, and I could say it's like, is this number even? And it outputs a 0 or a 1. It outputs a 1, the number is even. Good. So that's n inputs and n outputs. But Boolean gates act on zeros and ones, so an input and an output can be different sizes in terms of bits. So it could be 0, 1, 0, and the final output can be 1, 0. That's completely possible. But the idea is a unique input maps to a unique output. There's a one-to-one mapping, a one-to-one correspondence. It's surjective and injective, meaning it's bijective. All right. Okay. It's the definition of a function here. So when we're talking about Boolean logic gates, they can take either a 0 or a 1 or a series of zeros and ones as input, where n is a member of, and I is either a 0 or a 1. That's what this notation means. It's a member of a set. N is a set that has zeros and ones as its members. So let's call this I, actually. So an input is a member of, yeah, let's do it like this. It's a member of a set that has zeros and ones. An input equals I to the n, which just means it's a series of zeros and ones, n of these. You can consider this an alphabet, but then each wire input to an AND gate. So in other words, this can be a 0 or 1, this can be a 0 or a 1, and if it's 1, 1, if the input is 1, 1, then you get a 1, otherwise you get a 0. This is an example of an AND gate. And a NOT gate usually looks like this. Sometimes it's called an inverter. It takes a 0 or a 1 and it outputs a 1 or a 0, depending. It just flips the bit. So we can get into this, the nitty gritty of these later, but what I'm trying to say here is that a combinatorial circuit built out of these kinds of things is the simplest kind of computer you can have. It can't compute everything, but it can compute a large class of useful things for us. And we're going to build a hierarchy here, starting with this kind of computer. This is the foundation, combinatorial circuits. Now, you notice the one notable thing that this thing is missing is memory. When it gets these inputs and it gives an output, that's it, it's done, it clocks out. When you give it another series of inputs and it does another output, it does not remember this. It's as if that never happened. So there's no memory at all in combinatorial circuits. And it turns out a combinatorial circuit can compute any function, f of x, any function at all. It can be as simple as this, right? You can actually compute that. It can be x plus 1. That's called the full adder circuit. There's only full adder circuit, or x plus y rather, right? It can be a combination of two inputs and then it gives one output. It's built out of half adders, which I can actually show you. I'll put up some notes. They can actually be built out of like these gates, which is really neat. Essentially, like you put in the number in binary. Let's say you want to add these two together, and then it will actually do these combinatorial sort of combinations with these AND and OR gates, and the output will actually be the sum plus a carry digit. So like if you're adding 9 and 9 together, it'll output 8 and it'll output 1 as your carry digit. It's really cool. The idea is this is sort of the simplest class of computers, I want to say, or the more precisely the class of computers that can compute the least amount of things. So the space of problems it can compute, it's the smallest for this computer. So should I prove it? Yeah, we can actually prove that given these zeros and ones as an alphabet and given these Boolean logic gates, you can actually compute any given function. But you know what? Let's not do that. I'll put that in the notes. Okay, so right, what's the next step up? It's called a finite state machine, and it has these combinatorial circuits, yes. But it has a new ingredient. State. It has an internal state. And the state, each state can be represented by a symbol and an alphabet. And there can be 5 states. There can be 3 states. There can be 1. There can be 100. But it's finite number of states. And this is limiting. But it can do more than combinatorial circuits. What's a good example of a finite state machine? An interesting example of a finite state machine that has only state and doesn't have any kind of combinatorial circuits or anything like that is the controls for an elevator. It has only 2 states, up and down. And if it's in the up state, then it closes the doors. And it starts going up. If at any time it transitions to the down state, it knows that it will have gotten off at a floor. It will open the doors. And once people get off, it will close the doors again. There's just sensors that tell it whether or not that's other state. And then it will start going down. Pretty simple. What's a slightly more complicated one? A vending machine. You put in a coin. If it's in state, call it acceptor. It will allow money to go into the machine. If it's in the state paid, let's say, it will close the coin slot and it will ask for more input. And you input your selection here for whatever soft drink you want. Selection. And that's, we can say these states can actually have hierarchies, which is interesting. So you can say state selection, right? So we start in state acceptor. We put in some money. So it goes to state paid. Now it asks for your selection. You make a selection. It stores this in state. And then it dispenses the beverage based on this state. If it's in Coke state, Pepsi state, 7-Up state, whatever, it puts out a beverage. And then it goes back to acceptor state and it can accept more money. Right? That's not complicated. But a combinatorial circuit can't do it. A combinatorial circuit would not be able to do this. It would have a series of inputs, but it wouldn't know when to close or open the paid slot, and it wouldn't know when to dispense. What this thing does is it remembers previous operations. So it remembers whether money went in or not. It remembers whether or not a selection has been made. And it remembers whether or not the selection has been dispensed or not. So it has that memory. Combinatorial circuits don't have that, and therefore you wouldn't be able to make a vending machine out of purely combinatorial circuits. You need a finite state machine. Now, the finite state machine doesn't look like a computer so much, does it? And it's not. Your computer is not a finite state machine. Your computer is much more complicated than that because it has a memory bank and it has specifically a memory structure that's different than this, than just it's in one state, then it transitions to the next state, and there's rules for transitions between these states. It's if you get this input and you're in this state, and this thing is happening, you transition to the next state and you give this kind of output, something like that. There are more complicated memory structures and more complicated rules in this. The next step up in this hierarchy is what's known as a push-down automaton. And a push-down automaton has, in addition to these internal states, it has a stack of cells. And each cell, you can think of this as a magnetic tape or something like that, which it was in the very old days. And in each one of these, you can have one of these states. Or not states, alphabet. Think about an alphabet. Let's just use the English alphabet for simplicity for now. So this can be like A, B, Z, P, Q, and S. You can have in each of these states. And there's only two operations it can do. One is a push and one is a pop. A push means you put a new symbol in what is now the first, and this becomes the n+1. That's a push. A pop, on the other hand, means you dispense with the last element. So this would be the new stack after you pop. And these are actually a thing. JavaScript today actually has a push and pop operation for dealing with arrays. So certain simpler things can be computed by this. The class of problems that can be computed by this sort of thing is actually large enough to be useful and relevant to modern high-level programming languages. But it still can't compute everything because it doesn't have random access memory, right? So the next step up is a Turing machine. And a Turing machine can do more than just push or pop on this memory bank. It has like a little selector head, and it can be on a given cell at a time. And this thing can move around. It can select different memory slots to come to. And when it's on a certain memory slot, it can read/write to that memory slot. So if there's a symbol in here, like an A, it can say it's now a B. And it can move and do the same thing to all these here. And this still seems like a relatively simple machine here. You could probably even build it yourself out of most things you find in your garage, or a very slow implementation of it. But believe it or not, the Turing machine is what's known as Turing complete, which means that anything that can be computed theoretically is computable by the Turing machine. This is all it really takes. So this is the final level in our hierarchy, because now anything that theoretically can be computed is computable. So this, you might ask, well, what's not computable? And when I say something is not computable, I mean, no matter what, no automaton can compute it. That is, there's no device that you can give some sort of instructions and input to and walk away from the device, and the device does its thing autonomously and then provide some sort of output. This cannot be done by that device. It can be computed in principle by something that's not an automaton, but there's no way to do it. There's no way to compute it with a computer. That's what we're saying here. So, well, let's give an example of something that can't be computed, actually. This is called a halting problem. And the thing with the Turing machine is this is one of the reasons why it's such a useful theoretical tool, aside from showing these things that I just talked about before. But the Turing machine doesn't always halt. That is, in order to provide some sort of output and answer your question, the Turing machine, this thing here, needs to stop on a memory cell, and then it'll output the result of what's on that memory cell. So it'll output like a B if a B is written there. It doesn't always halt. It doesn't always stop. It can keep going forever and ever and ever and ever and ever, and be caught in this infinite loop and never actually output an answer. And those are undecidable problems. An undecidable problem cannot be computed. So if you ask the question, the computer won't be able to answer it. And whether or not a Turing machine will halt for a given initial configuration is actually an undecidable problem. So you can't tell whether your Turing machine is going to halt for a given problem. that's not computable. So if you ask a computer, computer, I have this memory bank, I have this state, I have this input. Can a Turing machine compute this for me? The computer will not be able to answer that problem. Little meta. That's like the human brain can't answer questions about itself, sort of thing. Um, so there you go. Those are the hierarchies of different computers, and this is what we really mean by a computer. But when we talk about a computer, this is the computer science approach, really, to the answer, what is a computer? But if we're going to start talking about classical computers and quantum computers, then this is going to require a more physicsy approach because these are, after all, physical concepts. So now that we know what a computer is, and by the way, there is a quantum Turing machine, there is a quantum finite state machine, there's all these kinds of things. There's this, what I just said about computers is generally applicable to both classical and quantum. But actually, not but, and there is another difference between classical and quantum computers that's physical in nature rather than computer sciencey in nature. The difference here is physical in nature. What a computer is the realm of computer science. It's an absolutely gorgeous theory because it's applicable to both classical and quantum computers, which is wild. Because the thing about how different classical and quantum physics is, and yet these models and all that I've said above is still applicable in general. So the difference between a classical and quantum computer is going to be physical rather than computer science. So remember what we just said, but further distinguished now. Is you hear in the news like a quantum computer. Wow, quantum computer. We built a quantum computer. What is a quantum computer? Because we have regular computers, we have classical computers. That's obvious. You're looking at this video on one right now. So what is a quantum computer? Well, it comes down to these three basic things: state, information, and computation. On a classical computer, these things are going to be very, very different than on a quantum computer. So let's briefly discuss state. Classical, and we're going to further refine this by saying deterministic state. Because there's also probabilistic state, there's stochastic state as well. So let's talk about classical deterministic state right now first. State initial. State final. There are two requirements for this. The first is that the final state, or even state at a later time, final just kind of means the output of one operation. We're going to talk about this very generally. So this could either be a physical system where each state moves to another state by F equals ma, or by a Lagrangian, or by the laws of physics moves states along. So you look outside right now, and I'm looking at this tree, and this tree evolves, the state of the tree evolves in time according to the physical laws. In a computer, it's evolving according to the program. The program are sort of like the laws of nature in a computer. But what I say is going to be applicable to both situations. And because we're talking about physics, I'm going to move back and forth between computers and physical systems. And of course, this is confusing because a computer is a physical system. But I'll cross that bridge when we come to it. But for now, concentrate on classical deterministic state. What does it mean? Well, it has a state, and the state at a later stage of evolution is deterministically predictable from the state at an earlier time. Okay, so in physics, it's F equals ma. Let's say we're using a very simple system. In a computer, it will be the I'm going to call them the laws of evolution. In our soda machine, that could be the laws that say, okay, you're in this state and you've just received this input. The law is that you have to give this output. Okay, that's all we're talking about. And the second thing is that a measurement of the current state does not affect the state. Does not affect the state. Okay, classical deterministic state. Um, Example. a die that's already been rolled. It's rolled and you got half of snake eyes. So if you roll the die and you just don't look, and then you do look, does the one change to something else? No, not really. When we start talking about information, this will be a little bit more subtle. Because if you roll a die, and then you don't look, you actually have less information than when you open your eyes and look and say, yes, it is on a one. But for state, the state that the thing is actually in, it's not affecting that in any kind of way. So classical probabilistic state. Two still holds. Two still holds. So measurement's not affecting. Doesn't affect the state. The first thing is now not true. You have initial state. You cannot predict the final state deterministically from this. All you can say is that there's a probability distribution that it can be in each of the possible states. So there's probability of this given state that it's going to be in this given state. That's all you can say about classical probabilistic state. Okay, let's talk about information now. Information is what an observer knows about a state, the state of a system. Information. Now, in a classical deterministic system, classical deterministic, state and info are not so different in this case. If it's deterministic, we can actually predict the final state from the initial state, so we don't actually really need to make an observation in most cases. If we have a basketball, as I say in the notes, and we throw it in the air, if we know the initial velocity, then we know exactly what the height it's going to reach is, maximum height. We don't have to make an observation, actually. We don't need to watch the basketball go in the air and come back down. We can just predict it. This is not true of probabilistic systems. So classical probabilistic systems, or let's say stochastic. These are different things, by the way, probability and stochastic, but it is stochastic as well as being probabilistic. I mean, unless you have like a very exotic process, but like non-stochastic computers, I don't think exist. And non-stochastic physics is not something in the realm that we're going to be really talking about. So stochastic slash probabilistic, stochastic information. All right, now we're gonna have to get mathematical. State and info are represented as a column vector. State one, state. These are lowercase s. This is lowercase s. Uppercase s is state. State equals dot 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 state n. Depending on how many variables are necessary to specify the given state of a system. If we're in classical physics, then the number of variables that are required to specify a 3D system are 6. Whoops. Are 6. 3D system. You've got x, y, and z, and you've got vx, vy, and vz. You can specify in other ways, but it takes 6. The information we have about a system is different, however. If it's a deterministic system like F equals ma, then you don't actually need to make an observation. So that's an example of classical deterministic information. However, the info on a state is a different thing when we come to probabilistic. Let's talk about probabilistic information now. We have this dice, and we rolled it. And let's say it's a 2 this time, which I guess that's the snake eyes equivalent of just one die. And we've just rolled it. It's like in a little cup. We're playing Parcheesi apparently, and we just kind of roll it, and it comes out in a 2. But we don't look. We don't look yet. How much information do we have about the system? What does our information look like? All we can say is that if it's a fair die, there's a 1/6 chance of it being in each place. So that looks like this. Mathematically, it's just a column vector. What about after we look? Well, it's a 2. 2, 3, 4. So it's definitely in the state of 2. It's absolutely not a 1. It's not a 3. It's not either of these things. So this is intriguing, and you'll hear a lot about in quantum mechanics of the collapse of the wave function. We've just seen the collapse of the wave function occur classically. So when the quantum collapse of the wave function is actually not a quantum feature, it's actually a classical feature. Because see, this happens right here. When I'm not looking at this die, it's in a kind of, you can call this a classical wave function of this information. We only know a probability distribution over the different states. And all of a sudden, when we do look, the state hasn't changed, but our information of the state has changed and it collapses to this. The difference in quantum mechanics besides classical reality is that in classical physics, we're not actually changing the state of the system. In quantum physics, we're actually, the information and state of the system are actually together. The best we know is the information about the system. So you are actually physically changing the state of the system when this collapse happens. That's the difference between quantum and classical. So that is a uniquely classical feature. That, for example, this die in quantum mechanics would actually be, the state would be in a superposition. It's not a 2. It actually is in this like weird superposition when we're not looking at it, of like a 1 and a 2 and a 3 and a 4. So you're not looking at it, it's actually in that state. In classical physics, when you're not looking at it, it is in a definite state. But when you look at it, you know that it's in a definite state. In quantum mechanics, information and state kind of gets together, and you can't really separate them too easily. So computation is left now. Computation. Just check my time real quick. How are we doing on time? Good. Good enough. All right. So doing pretty well on time here. Computation. All right. So computation are matrices acting on these column vectors of state to produce a new state. Computation acts on information as well as state. It acts on both of them. So we're going to talk about coins now and the flipping thereof. So a coin flip operation, let's start with deterministic computations. And again, this is all classical. We're all classical. Quantum is going to be the next lecture. We need a good footing in classical physics before we get into deterministic. Deterministic. Yeah. So we're not going to flip the coin. What we're actually just going to do is actually take the coin and just turn it around and put it down. And we know that the result of this is going to be it's in tails. That's what we intended. That's what we're going to do. We're going to carry out carefully in a way that the output is determined from the input. So that actually just looks like this. Let's say this is heads. Then it's going to give this, which is tails, and vice versa for the both. I can prove that because this times itself is the identity operator. So if we flip it to heads, if we flip heads to tails, we can then act again. And since it's the identity operator, it has to give back the initial, which is heads. QED. That's not super interesting because the state and information are the same. We can predict the state, the final state from the initial state. So we don't need to make an observation. So even before we flip this thing, we know what the output's going to be. When we do flip the thing, we don't need to make an observation because we know what the output's going to be. So our information and state are synced. Let's say we actually do flip this coin. What does a coin flip operator look like? It looks like this, actually. Why does it look like that? Well, because essentially there's a 1/2 probability of it not flipping and staying in the same spot, and there's a 1/2 probability of it flipping. This is just matrix addition. Hopefully we're all familiar with that. So that's what a coin flip operator looks like. And when you do that, you can actually have this kind of state, regardless of which column vector you're. So if you're flipping heads, you're flipping tails, it's this before we observe. And after we observe, it collapses into either heads or tails. So that's the information. This is info. We're talking about that. The state is definitely either heads or tails. Okay, so that's probabilistic versus deterministic computation. This is all classical. The next time we'll do the quantum analog of all these things, and that's going to kind of get to the heart of the difference between a classical and a quantum computer. So hope we all enjoyed. Have a great day. Have a great life. Keep learning and keep loving quantum physics.